Okay, let's start. So you have, what is it, math, online homework due? That's already due? No, that was the written homework. Online's due at 5 or at midnight? 5 p.m. today? So you got online homework due at 5 p.m. tonight. Then I'm going to give you kind of a heads up about the next online homework. The next online homework is about quantities that we haven't talked about in class, okay? But it's about you learning to apply this principle that if you want to write the accumulation function for any quantity, so I'll just call it, say, Q of x. So some quantity is accumulating as x changes, right? It's a function, right? So as x changes, you have different amounts of this quantity accumulating at various rates. And no matter what the quantity is, how do we write that accumulation function? So this is what we've been working on all semester. And so then in the next homework is you may be working with quantities that we never talked about in class. And the point of that is that you're now practicing this principle of it doesn't matter what quantity it is, I could still write the accumulation function. How would I write the accumulation function? Or what would I need to write the accumulation function for any quantity? The rate of change, right? So I need the rate of change of that quantity with respect to x. And how do I write the accumulation function? Raymond says integral, agree? Yeah, summing up little bits of that quantity, right? Summing up little, and how do we calculate a little bit of the quantity? Using the rate. What is it? Rate times change in x. But we need a different variable, right? So this is what? This is m dx, right? M dx, a little bit of the accumulated quantity, and we're going to sum all those up, starting from, not using our two function notation here. So in the next online homework, you're going to be applying this to quantities that we did not talk about in class, and that's the next skill for you, right? So that's the next skill for you, that I don't have to do a bunch of examples about pressure so that you can do pressure problems. I don't have to do a bunch of examples about population for you to do population problem. If you know the principle that you can write the accumulation for any quantity once you have its rate of change using our integral net accumulation function, then that's what you're going to be practicing in the homework, okay? Does that make sense? That's the next homework. Okay, so let's review. We're talking about work now. Let's kind of review a little bit where we've been here. So work is something applied over something, and how is it calculated? So work is force applied over a distance, right? And it's calculated by just the general formula for it. Force times distance, right? But then we saw it, so that's easy if you have a constant force and a straight line distance. If you have a constant force and a straight line distance, it's just like a, fourth grade multiplication problem. Force times distance. But things get complicated, right? As the force is applied, the force is changing. The distance could be curvy, right? So that's where we need our accumulation function, because we need to what? Sum up little bits of force. So what is our net accumulation of work? If I want to write accumulation of work, what do I need? What do I need if I want to write net accumulation of work? Yeah, the rate of change function, right? The rate of change. And we can use our integral accumulation function. So then the question is, what's the rate of change of work? What is the rate of change of work? And we figure that out by saying, okay, look, rate of change of work is based on what? dy equals mdx. But what is our input variable? S, right? It has to be in the direction that the force is applied. So if this thing is, it's a curve, it's an arc, then we need that ds, right? ds is like tangent to the arc. We don't want dx if my curve is coming along like this. Then I need ds, right? So okay, and so what did we, so then if work is force times distance, in order to find the rate of change, we can say dw equals rate times ds. Well, what is ds? ds is a little bit of distance. Therefore, the rate of change of work is? A little bit of work is? What does that have to be? Based on the fact that work is force times distance. So a little bit of work is the force at the moment times the little bit of distance. So we saw that the rate of change of work was force. Force in the direction of motion, the direction we're going, right? That's why it's RWS, right? Times a little bit of distance, ds along the arc. Okay, so sorry. Let's try this. There we go. So this is our force times distance for work. Okay, and so what was this for the first pushy ant problem? We had a constant force in the direction of the curve. So then what was this about? Why did we need this? If this was the force in the direction of S, in the direction of the curve, why did we need that? Do you remember? What's that? Yeah, but so then what does it do then? Yes, that's true, but what does it do? Remember what it did for us? What is the independent variable of work here? X, right? So we said the x coordinate of the ant, right? So we wanted work in terms of what's the x coordinate of the ant, not how far the ant has gone. So this right here was like it was a transformation from in the s direction to in terms of x, right? So this thing transformed us from force along the direction of the ant to turning it into a work as a function of the x coordinate, horizontal distance. So this then was f of x, force according to the x coordinate of the ant, as opposed to the distance traveled. So we need, what do we need? We need the force, just in general now, work is always going to be integral of force dt, where this is force, a force function as a function of x coordinate. So then we got to the second one, so let's take a look at that. We got to the second situation where the force was changing. Not only was the ant walking on the wavy path, but the force was increasing as the ant walked, like maybe some dust or something was accumulating on the seed the ant was pushing, and so the force required increased. So let's take a look at where we were here. Okay, and so then the rate function, and then we said the force was given here. F2 of S, right? So F2 of S was the new force function, a changing force according to how far the ant has walked, S. So we need, so the rate is going to be f of x, okay, which is going to be f of s times the transformation. This thing. This. Okay, so that's what we said. So we got the force in the force as a function of s, transforming it to get it in terms of x. Okay, and so then how are we going to get, where does the s come from? Well, s comes from our arc length function. So I'm going to substitute in that s right there into our force function. And this should be x. Okay, so there it is. So there's force along the path, but in terms of x, and then times our thing that transforms us from ds to dx, right? To give us the x position. So then what happened was, so I'll get rid of this part then. So now we got it. So there's the rate function. So I put this rate function, we graphed the work function. We set up the work function as the integral of the rate, and I was graphing this work function. But what happened was there was one little mistake right in this here, right here. So here, A, in the, say, we're defining a function, A is what's called a dummy variable. It's a placeholder for one of our arguments. So this tells it that whenever I use this function notation, it's going to grab that right there and it's going to put it there to calculate the value of it. Okay? So now up here, now I'm defining this function, but I'm using the function notation here. So now when I'm using function notations, it's expecting values. It's expecting something there, something there. This is the dummy variable for the rate, but now it's expecting something for A. And when you don't tell it, GC, what it is, what is it? Yeah, it's going to be 1. So when I come here, I need to specify what it is I want A to be. I don't want it to be 1. I want it to be 0. Okay, so now the rate function is correct. 0 there. And I can come over here, and now when I graph it, it should be, lastly, you can watch the video. All I do is switch that A to a 0, and the graph came right up. But now there's some other mistake. Okay, but anyway, so this work function, because the force was increasing the whole way, it meant more work the whole way. So you can watch the video. We got this graph that was up like this. And so it was more work the whole way. F2.
Yeah.
Thank you.
Yeah, and
Did
then
the student say
crashed.
that?
No. I was looking at the back.
Oh, okay.
How is it to do this? And yeah, it takes time like to graph it, but it does.
There we go. Thank you so much. So what is weight? What is the weight of something? The weight of something is actually the force that gravity pulls on it. All right, the force with which gravity pulls on it. That's weight. So the force of gravity on an object is the object weight. Okay? So alternatively, the object's weight is the same as the force required to keep it from falling. Okay, or to maybe lift it steadily. Okay, so if you So the weight of my phone is the force of gravity on it, and I'm supplying an equal and opposite force upward to keep it from falling. Okay, so the weight of the phone is the same as the force that I'm applying to keep it up and not let it fall. Okay, so weight then, whenever you're talking about the weight of something, it has force units. So in metric, that's newtons. In English, that's pounds. So kilograms, is that weight? Kilograms. We sure use it. We sure use that terminology like it's weight all the time. We think and talk kilograms as weight, but it's not. It's a different. This is apples and oranges. Truly, kilograms are not weight but mass. Okay, mass is just a measure of how much matter. How much matter. Whereas weight is the pull of gravity on the matter. So kilograms is not weight. Okay? Kilograms is not weight, it is mass. So in metric units, the metric units for weight is newtons. Okay? But we have to fight against, culture and everyday language and how we've been conditioned to think that kilograms is weight. It's not. It's mass. And if you want really truly weight in metric units, you're talking about newtons. Okay, newtons and pounds. So we have to really practice breaking our thinking about kilograms being weight. All right? So weight in the metric system then, since it's force in newtons, it's calculated by mass times gravity. So this is how you would, given the mass, how you would get weight. M is the mass of the object in kilograms. G is the acceleration of gravity. So G for Earth is 9.8 meters per second per second. So in problems, if you're given the mass in kilograms and you need the weight force, you need to use F equals mg. But if you're given pounds, there's no initial calculation to do because that's already weight force. Does that make sense? So you may see the same type of problem in English versus metric units. When you're in metric units, if you're given kilograms, you need to get weight, you need to do this initial calculation of mg, and that gets you weight in newtons. But if you're given pounds, you don't do that. You don't do an mg calculation because pounds is already weight. It's already force. Does that make sense? Okay, so that's an overview of pounds versus mass, and weight is the force of gravity. So let's look at an example here. Okay, so a winch, so we got this problem here. So a winch lifts a platform from the ground to the top of a building by a thick cable. The rate of change of the cable weight is 151.77 newtons per meter. The platform structure weighs 28 15 newtons. The winch must lift the floor of the platform 93 meters for people to step onto the building's top. Okay, so our goal here, define a function W whose values WH give the accumulated work at each height h above the ground as h varies from 0 to 93. So you see that this is a force applied. So if I'm lifting something, I'm applying a force, right? Because weight is force. So I'm applying a force to lift it. The force is the weight, the current weight, and we're applying force over a distance. So this requires work to lift the platform. So when you come to a word problem like this, rather than just like focusing on the numbers and thinking like, what formula do I need? We want to kind of really understand the situation, maybe define all the quantities involved. So let's just kind of brainstorm on the important quantities in this. And so a quantity, for instance, is, temperature or volume. Volume, so like here's some the temperature outside. This is a quantity, and maybe it's not really important. In degrees Fahrenheit. That's an example of a quantity. The volume of the wooden platform, of the wood deck, in feet cubed. These are examples of quantities, probably ones that we wouldn't really care about in this problem. So let's just brainstorm on what are some possible quantities that might be important in this situation. And even if it's not something we use in the end, that's fine. We're just going to write down as many as we can. So actually, I want you to do that. I want you to get a partner. Everyone's talking with someone, and just try to come up with like maybe 7 quantities that may or may not be helpful in this. But if you know they're not helpful, we don't want that. So 7 quantities that might be helpful in solving this or modeling this problem. Okay? So everyone's got a partner. And if you need a partner, then Derek and Pollock, yeah.
In that.
So the rate of change of cable weight.
Okay, so numbers really aren't involved here when you're doing this. You're just brainstorming on the quantities themselves. For instance, temperature outside in degrees Fahrenheit, volume of the wood deck in feet cubed. That's all we're getting at here. So what just general quantities are part of this situation that will help us model this in terms of work, the work accumulation of work. So that's what we're getting at. Okay, let's see what you came up with. What was a quantity that you thought would be helpful in this situation? Chauncey? Initial height. So the height, how about the height of the platform? In what? In meters. I think this is certainly going to be helpful or important, right? And then they said that, they told us that was h, right? Height above the ground, h. Okay, what else? Other quantities that's going to be helpful in this situation or involved? Yeah, Tia. The force, so when you say the force of the cable, so there's, so like the weight of the cable? the force of the weight. So there's like two different things that you're kind of like overlapping there. There's the weight of the cable, which is a force, and then there's like the force that the winch is pulling with. Is that right? Okay. Yeah. So is that what you meant? So the force on the winch, or the force the winch is pulling with. And what's the units on that? In? Okay, so that's talking about the weight of the cable. Newtons, right? And that would be, how would we symbolize that? The force on the winch in newtons. Is that changing or constant? That's changing. So it's like a force function, and we want it to be a function of what? H, right? So that force on the winch in newtons, that's going to be a function of the height of the cable. Why? Why will it change? Why will the force on the winch change? Yeah, because is the cable weight changing? What is changing that creates a variable force on the winch? And how does the height change the force on the winch? What is it that's creating and is it increasing or decreasing? Decreasing because? So it's because the length of the cable is shortening, right? The length of the cable. The weight of the cable stays the same. It's that 151.77 newtons per meter. But then because there's less cable, so maybe that's what we want here. So we want another quantity, the length of extended cable. Is that what they call it? Cable, yeah. In what will that be in? And maybe we just call that L. Okay. Who else had a quantity that was going to be important in this modeling the situation? There's another big one, super important. Yeah. So the platform. Okay. So eventually we're going to need weight. So rather than, yes, the mass is good, but then we're going to need weight. So I'm just going to jump right to weight. So the weight of the platform. And what will that be in? Newtons. Is that constant or changing? Constant or changing? That's a constant, right? So we could assign a letter to it, or we could just know what it is. What is it? Is that the 2815? All right, there's another biggie here that we're leaving off. What other big quantity is really important here? Yes, sir, in the back. Okay, the acceleration of gravity? Is that what you mean? Constant or changing? And what is that? 9.8 meters per second. There's still another huge one that we're leaving off. The radius of the winch. Okay, can write that down. I'm not sure we're going to need it, but what is the focal quantity of this problem? Yeah, sir. Rate of change of weight of the cable. Okay, and we know that, so I'll just put a box around it. Still, what's the focal point of this problem? What quantity? Work, right? So what are we after? We're after the accumulated work done by the winch. In, what are the units? Newton meters. And those are also called joules, or J. So a Newton meter is a joule, that's capital J. Okay, and so if we're after accumulated work as a function of height, we're saying we're going to accumulate, we want to know the accumulated work since, so we could say since any height, so we could start with A. Accumulated works from any height to the current height, from any starting height to the current height. And what will be our, how will we model the amount of work? How do we get the amount of work? What is that? Accumulated work. Sarah?
The integral from A to H of the rate of change of work times dt.
Good, right? Any quantity. All you need is this rate of change, and you can write the net accumulation of that quantity by the rate times dx, or whatever or the integral of the rate times dx. So yeah, so that's a, not a w. So what do we need? We need the rate of change of work. And what did we say the rate of change of work was? Evelyn? Force. So the work that the winch does is going to be the integral of the force on the winch, dt. So based on our quantities here that we've defined, we have to figure out what is the force on the winch. What is the force on the winch? Or, so once we can come up with this f of t function, which is really what, f of h. We have that f of h function. It goes there, and we've got a work function. And we've modeled the accumulated work. So we got to write this f of h function. So how are we going to write the f of h function? What will be the general structure of that, calculating how much work is on that winch? Well, in general, how much force is on that winch? Comes from what? Where does the force come from on that winch? What's that? The platform is going to put how much force on the winch? So it's going to be the force from the platform. Anything else putting a weight on the winch? So the rate of change puts force on the winch. What else puts force on the winch? Well, yeah, all forces are gravity, right? All forces are gravity. But besides the platform, the cable weight, right? So what am I going to do with the cable weight? I got the platform weight, cable weight. How do I get the total force on the winch? Add, right? Add. Isn't it just going to be the sum total? It's going to be the sum total of how much force or weight of the platform plus how much force or weight from the cable. Fixed or changing? Fixed or changing? This one. So what I'm circling. Fixed or changing? Changing because of the length, right? So this force of the platform, 2815. All we have left is to do is get the force of the cable, right? So we have L meters out, but we need this as a function of h, the height, right? H meters. So how do I get, what do I need? I need the weight of that cable, and we defined it as L meters of it in terms of H. How will I get that? How will I get that? So first of all, what is L in terms of H? Well, how much cable do I have out if the platform is H meters up? He wants 93 minus H. Agree with that? That's a good start. So what is the weight in newtons of 93 minus H meters of cable? How do I get that? Well, here the cable weight is what? 151.77 newtons per meter. That's a rate of change. And what does a rate of change mean? It means given any change in meters, we can find the newtons by doing what? See, we can use our dy equals mdx for this. So that 151.7 is a rate of change. It means for any variation in meters, I can calculate the weight by doing what? Multiplying the rate times the variation in meters. Okay, and that gives me that would give me my weight of the cable. So I can take my rate. What is my variation in meters? H? (93 minus H), right? So this is kind of like, this is my variation, like my dx, times the rate, gives me d force of the cable. So this was my f of h function. And that force as a function of height, that's my rate of change of work. So now I'm ready to write the work function. So work is integral from a to h of so I could write f of t dt, having defined f as this. This is my rate of change of work. So look, I have a rate of change within a rate of change, right? I have a rate of change of what? Weight or force. And I use that to calculate the force of the cable pulling down on the winch. And then that force is itself a rate of change of work. And so then I use that to write my work accumulation function. So how would I get the total work that the winch so what's the work that the winch exerts to lift the platform the last half and also the whole way? Okay, so how do I, if I want to put this in GC? I can define the force function as (2815) plus 151.77 times G minus H. Cool. Looking good so far? And then I can do my work from A to H equals integral what of f t dt. Okay, now I want to know how much total work is accomplished by the winch to lift the whole platform. So what's the total work accomplished by the winch to lift the whole platform? What should I do? going to use my function notation and go from 0, 93. So yeah, so Newton meters are kind of, let's see. Is that 91,810 joules? Well, so this is yeah. So this is a lot of work because it's a what? It's a elevator lift lifting people and heavy cables, right? So we could also use kilojoules. So like 91.8 kilojoules. Okay, so the work that it does for the last half, from a halfway point up to the top, half the amount of work of the total? Is it half? Is it going to be less? If it's not half, less or more than half? Why less? What's that? Less cable, right? So in the second half, the force on the winch is less because less cable that whole way. So let's see how much it is. How would I find out? I want to know the second half from the midpoint up to the top. How much work? What should I put in? He wants 46.5 to 93. There we go. That's what I want. Oh, so I did not move my decimal point right here. This was actually 918,000 joules. Or 918 kilojoules. All right, and this is basically 295 kilojoules. Less than half? Way less than half, right? Way less than half to do the second half because of all that cable extended in the first part there's a lot more force on the winch, so it takes a lot more work in the first half compared to the second half.
Question.
Please.
When you define the force function,
Yeah.
should you, that's just the weight of the platform, that's not the work done by the platform, don't you need to do that work by the height?
But that's what we're doing the accumulation of work here. This is the force function on the winch, not the work function. This is the weight. This is the weight on the winch, which is the force. That's our rate of change of work.
Okay.
So I'm not calculating the work here. I'm calculating the force on the winch at any height h. And that force is the rate of change of work. Make sense? Other questions?